Previously, Gemma 4 architecture overview. Today, real depth on the most important architectural choice. Dense versus mixture of experts. Starting with dense. Dense transformers work like this. Every token entering the model activates every parameter in every layer. All compute, every time, no skipping. This is the traditional transformer design. The engineering consequence. Each token costs the full parameter count in compute. A 12 billion parameter dense model does roughly 12 billion operations per token. Compute scales linearly with model size. The flip side, dense models use memory efficiently. Memory equals parameter count. Every parameter loaded is being used. No idle waits, no routing overhead. Memory usage is predictable. Where dense wins. Memory is tight, compute is available. Latency must be predictable. No routing variability. Smaller models for mobile and edge. Most edge scenarios actually fit dense better than people assume. Dense models, every parameter, every token, predictable behavior, memory efficient. But there is another path. Mixture of experts takes a different approach. That is next. Previously, dense models activate every parameter per token. Today, a different design. Mixture of experts, selective activation, different trade-offs. MoE works differently. A token enters, a router examines it. The router picks which expert should handle this token. Only the selected experts activate, the others stay dormant. The compute win is real. Only the active experts do math. A 12 billion parameter MoE might only activate 4 billion per token, roughly a third of the compute. Faster inference. But here's the catch. All experts must be loaded in memory, even the dormant ones. The router can't pick what's not there. 12 billion MoE still needs 12 billion memory. And there's a third reality. The router itself takes time. Every token requires a routing decision. Routing variability adds latency unpredictability. For real time, this matters. MoE, less compute per token, but same memory burden, plus routing overhead. Different trade-offs from dense, not strictly better. Next, the real engineering numbers. Previously, the mechanics of MoE. Today, the real engineering trade-offs across 4 dimensions: memory, compute, latency, quality, practical numbers. Memory first. A 12 billion dense model and a 12 billion MoE model use the same memory, about 24 gigabytes at full precision, about 12 gigabytes quantized. MoE saves compute, not memory. Compute per token. The 12 billion dense model does 12 billion operations per token. An MoE of the same total size typically does around 4 billion operations per token, roughly a third of the compute. Latency behavior. Dense models give deterministic timing, same work every time. MoE routing introduces variability. Different tokens hit different experts. Where predictable timing matters, dense behaves better. Quality is where MoE shines. A 12 billion MoE typically matches the quality of a much larger dense model, often 20 to 30 billion equivalent, while doing the compute of a 4 billion model. The summary. Memory cost is equal. MoE wins on compute and quality per compute. Dense wins on predictable latency. Different trade-offs for different deployments. Next, when to pick each. Previously, the 4 trade-offs. Today, the decision framework. Concrete criteria. When dense wins, when MoE wins. Pick dense when you need predictable latency. When memory is tight but compute is available. When the model is smaller, under 7 billion parameters, MoE rarely beats dense. Most edge deployments fit this profile. Pick MoE when compute is the bottleneck and memory is abundant. When quality matters more than predictable timing. When the model is large, 40 billion parameters or more, MoE wins on quality per compute, common in cloud. The edge reality. Memory is constrained. Latency must be predictable. Most Gemma 4 sizes are dense. The architecture fits the hardware. MoE isn't better than dense. It's a different trade-off. Pick based on what your deployment actually needs. That's engineering judgment, not hype. Dense versus MoE. Real trade-offs, real production decisions. Episode 4 complete. Subscribe to follow the series. Episode 5 next, quantization, where Ion 4 actually beats FP16. Recap: dense for predictable latency and smaller edge models. MoE for compute-bound, quality-critical, larger cloud deployments.